First, start by subscribing. The process of building a quantum computer. Computers are a revolutionary technology that processes information in a different way than conventional classical computers. Building a quantum computer requires a complex scientific and technological process that integrates knowledge from a variety of fields and computer science. In this article, we will go through the process of building a quantum computer step by step. 1. Design of a quantum bit qubit. The basic unit of a quantum computer is a qubit. Must be able to have a superposition state, meaning it can be in both 0 and 1 states at the same time. There are several ways to implement qubits, the main ones being superconducting qubit. A qubit made of superconductors that creates quantum states by controlling the flow of current at very low temperatures. Superconducting qubits are currently the most widely studied form, with IBM and Google using this approach. Ion trap qubit. A method of creating qubits by trapping ions in an electromagnetic field. The energy state of the ion can be manipulated to create a quantum state, and ion qubits have high accuracy and long coherence times. Optical qubits. A method of using photons as qubits, suitable for applications in quantum communication and information processing, studied in areas such as quantum cryptography. 2. Design of qubit interactions. Qubits must be able to be entangled with each other, must be designed. And for this, entanglement is essential to maximizing the computational power of quantum computers. Here are some ways to implement interactions between qubits. Quantum gates used to manipulate the state of qubits, changing the state of each qubit or creating an entangled state. Quantum gates come in many forms, the most common of which are the CNOT and the phase shift gate. Interaction mechanism. We need to design a physical mechanism that defines the interaction between qubits. For example, in the case of superconducting qubits, the interaction can be controlled through coupling between qubits. This process requires precise control to generate the desired quantum state. 3. Quantum circuit design. The calculations of a quantum computer are done through quantum circuits. Quantum circuits are made up of a combination of qubits and quantum gates, which define operations to solve specific problems. The process of designing a quantum circuit is as follows. Select an algorithm. Choose a quantum algorithm that fits the problem you want to solve. For example, you can choose Shor's algorithm or Grover's algorithm. Circuit configuration. Configure a quantum circuit by combining qubits and quantum gates according to the selected algorithm. In this process, the order of each gate and the entanglement state between qubits must be taken into account. Simulate the designed quantum circuit to verify the expected results. This allows us to evaluate the accuracy and efficiency of the circuit. 4. Environmental control and cooling. Quantum computers are susceptible to the influence of the external environment, so an environment is needed to control this and keep the qubits stable. The process is as follows. Temperature control. Many quantum computers operate in cryogenic environments. For example, superconducting qubits must operate at temperatures below about 20 mK Kelvin. So equipment such as helium coolers are used to maintain the required temperatures. Noise reduction. Install physical protection devices and electromagnetic shielding to minimize external noise and contributes to maintaining the state of the qubit stable. 5. Quantum measurement. In order to obtain the calculation result of a quantum must be measured. Quantum measurement is the process of collapsing a superposition state into a single unique state. The process is as follows. Design of a measurement device. Design a device to measure the state of a qubit. Since measurement results are generally determined probabilistically, statistically reliable results are obtained through multiple measurements. Interpret results. Interpret the measurement results to extract the desired information. In this process, the results must be analyzed according to the initial state of the qubit and the nature of the algorithm. Error correction. Quantum computers are sensitive to noise, and correction techniques are needed to compensate for this. Quantum error correction is essential to protect the state of qubits and increase the reliability of computations. The main methods are quantum error correction code, a method to detect and correct errors by encoding the state of a qubit into multiple qubits. Typical error correction codes include Shor code and Stein code. Feedback mechanism: design a feedback system that monitors the state of the qubit and automatically corrects errors when they occur. This contributes to increasing the accuracy of calculations. 7. Commercialization and application: the ultimate goal of quantum practical applications. To fully exploit the potential of quantum computers, we take the following steps. Industry collaboration: working with companies and research institutions to explore the commercial potential of quantum computers. Big companies like IBM, Google, and Microsoft are actively researching in this field. Software development: develop programming languages and software tools for quantum computers, enabling researchers and developers to easily implement and experiment with quantum algorithms. Exploring applications: explore the many areas where quantum computers can be applied. For example, we study its potential applications in cryptography, materials optimization problems, medicine, etc. Conclusion: the process involves a complex process that starts from designing qubits to constructing quantum circuits. Controlling the environment, measuring, correcting errors, and this process requires a convergence of physics, engineering, and there are many challenges that must be addressed before quantum computers can become practical. If you subscribe, I will do my best.